Akhawayn University. I will be presenting a work on nanocoating and testing of CSP reflectors that are suitable for the Moroccan environment. So this work was financed by IRSEC. So first of all, I have to thank the people who financed the project. So this is the IRSEC institution, and also thank the people working and our partners in the project, mainly Professor Nawi and Professor Ben Youssef and Talib. So those people really allowed us to use their facilities and help us to succeed in doing this project. I also don't forget to thank Dr. Nasiri. This is most of the work is her PhD work. So if we look to the Moroccan consumption of energy, we can see that we are in a growing economy. So the consumption of energy is growing each year by 7%. So, and if we look to the total primary energy supply of Morocco, it is mainly done by 70% of oil, 16% of coal, and just 8% of biofuel, and natural gas 6%. The problem is that most of the energy is imported. So 90% is imported from outside the country, which is not good, and we don't really do very well in that. So the future of Morocco, of course, is in renewable energy, and as the Moroccan citizen and the scientists, we are really interested in improving and doing some improvement in this direction. So our work is on solar concentrated power systems, because we know that in Morocco we do have very good conditions for this technology, and we already started having many interesting projects in that sense. So as you know, most of you know that the working principle of the concentrated solar power plants is having some reflectors that concentrates the sunlight in a receiver, so you generate heat and you generate steam and have electricity. So you can see that the mirror is a very important parameter in all kind of CSP power plants, so in the line concentration or in the point concentration. So we are really interested on the mirror. So of course there are plenty of limitations on the good functioning of the mirrors, because most of places that are suitable for the application of, or implementation of CSP plants are mostly desert area, where you have a lot of accumulation of dust, and you don't have also lots of water to clean the mirrors. So our work is to prepare some mirrors that are very reflectant, okay? So this is a very important thing. They should be very reflectant, and in the same time they should be super hydrophobic or super hydrophilic and self-cleaners. So means that they will have ability to, if you have like water that come on the top, they will just spread it on the top and then clean the surface, or they can make it like small droplet that can also take the dust with it. And we also looking for some other coating that are able to degrade all the dust. So this is our project, so creating the super hydrophobic. So if I will see normally the mirrors that are in the market, you have two types. You have the first surface mirror and you have the second surface mirrors. So the first surface mirror are the ones where you have the silver directly to the air, I mean it is on the surface to the climate. and the other kind of mirrors are the ones with a glass protecting layer. So of course the first one, where you have the silver directly in contact to the sun, in front of the sun, is much more reflectant, and the other ones are less because of the glass on the top. The other thing that you have, when you have a glass surface on the top, you will decrease the flexibility, because in this case you can, in the case of the first surface mirror, you can make the deposition on different kind of substrate, not just the glass, which may give you a lot of freedom in choosing your substrate. So if I compare the second surface mirror reflectance and the first surface mirror, I can see that the surface, the first surface mirror, of course, is much more reflectance than the other one. So if I just speak briefly about the effects of superhydrophobicity and superhydrophilicity, is a phenomenon that we just inspired scientists from nature. So this is the lattice effect, which is inspired from lattice flower, where you have the droplets of water just stay on the top and they don't really spread, and this is because of the double structure that you can see here on the surface. So, and it can be, the double structure can be in the micro scale or to the nano scale. Of course, in our case, we will be struggling between these two properties, because we are looking for super reflectance, means that you will keep the super reflectance on the high reflectance, so we need to have a very transparent top layer. But when we will work on making this structure, we will lose on the transparency, okay, because you have some dispersion on the top of the surface. You can also have super hydrophilicity, means that the water will spread and also can clean the surface. So the candidate material that we choose for this work was the aluminum oxide or titanium dioxide and zinc oxide as top layers. Of course, we also prepared the mirrors that are silver on copper and on the thin substrate, which is the glass. So we choose the three materials because they are easier for their facility to make the deposition, and because of their very interesting parameters like properties like high hardness for the aluminum oxide, their transparency. So the titanium dioxide, the zinc oxide also have another property, which is the photocatalytic power. So they can degrade the dirt. So we did all the depositions by means of the Elgar technique. So at low temperature, you see here that you are using a temperature around 500, 400, because also we have to think about the metal, which is the silver, so we couldn't exceed those temperatures. So this is the technique. So in Elgar technique, you have the precursor that you nebulize into small droplets, and when they are blown in the air, they will be transported by the nitrogen and deposited on the substrate at a given temperature. So you can have different thicknesses, and this is what you will see in the work of Huda. If you are interested, she did the different thicknesses and worked with different temperature to see the effects on the structure and the surface of the thin films. So these are the X-ray, XRD spectra of the three materials. You can see that aluminum oxide was amorphous, of course, at this temperature. And we have the titanium dioxide, which is anatase. You have a hexagonal wurtzite for the ZNO. So if we look to the specular reflectance of the mirrors, we can see that we did well with these three, layers, you can see that the spectral reflectance in the near infrared, which is important for this application, is around 94% and 95%, which is very, very good. So we worked we looked to the wetting properties by means of the Cecil drop or contact angle, and we saw that the contact angle was on the order of 102, means that the aluminum oxide is hydrophobic. And if we look to the roughness of the surface, the roughness is quite low. This is why we didn't have very high, let's say, hydrophobicity of the aluminum oxide. So still work is going on to see if we can gain in roughness while keeping a good transparency. Here we look to the titanium dioxide and the Zn oxide, and you can see here that you have some higher roughness compared to the Zn oxide, and we can see also some double structure for both of them, and this is explaining the fact that when we put the droplets, we see that a total spreading of the droplets on the surface, and this is really creating the super hydrophobicity. Means that these two materials are very interesting in terms of the coating of the mirrors. So there are plenty of work done by Huda. If you are interested, you can see her presentation where you can see the effect of the temperature and the thickness on Zn oxide and on titanium dioxide. So we also studied the effect, the photocatalytic activity of these two thin layers, and we saw that the methylene blue degradation for different hours was much more interesting for the case of Zn oxide, and we see that after 5-hour exposure, 42% of the methylene blue was already degraded, which is good. So Zn oxide was much more interesting. So of course, until now we saw all the mirrors and we saw the same techniques, but until now with the Elgar we were not able to get to super hydrophobicity. We really wanted to see it in some of the materials. So in literature we found out that we can do it with more easily with the low temperature electrochemical deposition that we did. So we did it and we sputtered ZNO thin films on the surface, so we created the double structure, and then we were able then to get to a super hydrophobic surface. But this surface was really changing from super hydrophobic to super hydrophilic very easily under exposure to UV light. So, okay, until now, you saw that we prepared the mirrors, we prepared the nice coatings, but what about their life? Are the mirrors able to withstand the Moroccan environment? So this is why we we saw different like aging tests that you can see if you will see the presentation of Hussam. He is presenting his machine about the design of sand abrasion chamber. So usually all these other techniques for UV, spray salt, thermal shock are technique that like described in the literature, but for the sand abrasion is not really well done. So, and there's still work to do there. So we were working on making our sand abraser machine, and we designed it by following the military standards, and he used like a vertical support, so you can see, and he designed it to be with the following using SolidWorks. So after the preparation of this sand blower, so with this sand blower we are able to get sand from different regions from Morocco and apply it to the mirror and see the effects on the surface. So we did some experiments. Of course, this is just one slide from the experiment that we did, and you see that really the effect of the sand on the surface. We had some sand from Ouarzazate and from Bengrir, where we did the experiments, because this was built in the Green Park. So we can see that the roughness increased with 450%. So really, a lot of damage on the surface under abrasion of the sand. So of course, if we want to know the lifetime of the mirrors in different regions of Morocco, we should look for potential regions of installation that are suitable for the installation of this kind of plants. And we did a statistical study about the region of Morocco, and using the data, the satellite data, and also the measured data from Earth. So, and we calculated following the several models. So here you see so you see that we choose 4 regions as candidates for implementation of the CSP plans, and we can see that Missour, Erfoud, and Zagora was the best region for this installation because of the high direct radiation, which is higher than 2000, and also because of the lower density and of population, and also for the flatness of the surface. But the region of Tantan was not good because the radiation was also low, and because the humidity is quite high in the region. So, as a conclusion, this project was it's just opened. We reached many of our objectives, but it was like an opening for plenty of ideas and research. We are still doing a lot of research on improving the surface of the mirrors still, and also in improving and making a good aging test for the mirrors in the Moroccan environment. And what we found here on the mirror can be also applied for a PV, of course, the surface of the PV. And thank you very much for your attention.